series. Today, it's my great pleasure to welcome my long-term collaborator, Maja Rudolph, who is a senior research scientist at the Bosch Center for AI, where Maja works on machine learning research, questions which are derived from oftentimes engineering problems. For example, how can we model driving behavior? How can we do forecasting? And how can we find anomalies in for example, a series of sensor data? And today, Maja will present about some of this in her talk, I'm sure. So Maja has a PhD from Columbia University, where she worked with David Bly. And prior to that, she did her undergraduate degree at MIT in mathematics. So I very much look forward to your presentation. And Maja, take it away.
Great. Yeah, Stefan, thank you so much. Yeah, it's really a pleasure to be talking to you guys, since, as Stefan mentioned, we are like long-term collaborators, and especially in the past year, we've been working a lot together on anomaly detection. Today, I'm talking about some other work, though. So this work was done by an intern, Mona Schirmer, who did her master thesis with me last summer. And yeah, so this is basically the result of this collaboration. And the topic was how to develop a neural architecture that can, in a very good way, handle time series with irregular time intervals. And so we developed the continuous recurrent units, and this is what I want to present to you guys today. Yeah, so today I'll be talking about irregular time series. They're ubiquitous in many different applications. So for example, as Stefan mentioned, I work at Bosch. That's an engineering company. And in many engineering applications, the sensor data comes in at irregular time intervals. And this also carries important information. So for example, if you have mobile robots in a factory plant interacting with a mobile network, then the times at which they send information to the networking points come in usually at irregular time intervals. Or another application domain where this, thinking about these kind of time series is very, very important, is actually in medical applications, right? So we go to the doctor not at regularly tacted intervals, but when we feel bad, when we're sick. Certain lab measurements are asked for certain reason at certain time points and so forth. And so for powerful personalized medicine applications, we need predictive models or sequence models for other modeling tasks, which can somehow model time series where the timestamps might be irregular, and somehow exploit this information of how much time has passed between observations in a principled manner. Yeah, and so here I'm starting to introduce some notation. So we will typically talk about the time series X, T, and T is the index set of the timestamps when we observe. And at each time point T, xt might be multi-dimensional. So could be a 10-dimensional, could be a 1,000-dimensional time series, or could be video frames that come in at these time steps, T0 through Tn. Yeah, and so before I present our work, I want to kind of place it in a landscape of related work. So first of all, there are a bunch of different recurrent neural networks. And traditionally in the 80s, the first formulations of recurrent neural networks, they were often in continuous time. But yet all the practical implementations and the the RNN architectures that we use today, they usually assume a regular spacing of the time intervals between observations. And so, yeah, divide the related work into these like discrete time models that don't really have a notion of dynamics between observations. Then there are also continuous time models. So for example, their quite popular recent line of work are neural ODEs. Those are ordinary ODEs, ordinary differential equations, whose parameters are parameterized by neural networks. And so based on these neural ODEs, there are actually some really interesting sequence models in recent years, like for example, latent ODE or ODE RNN and ODE LSTM, which are kind of use these ideas from neural ODEs to get a continuity of the latent states. And thereby they're able to model irregularly sampled data. One criticism that RNNs get in some sub-communities is that their latent states are not really stochastic. And so this really limits the type of sequences that can be modeled with like a vanilla RNN. And so another, let's say, subset of RNNs that are maybe related to our work are methods where the latent state has some kind of probabilistic interpretation. And specifically, there are like some works that are variations on deep Kalman filters. So there's a latent state, and in this latent state, there is a Kalman filter. And then I also want to mention the Kalman filter specifically, which is the optimal filter for this like linear Gaussian state space model. And then finally our work is here. So it's on, this is the CRU, the continuous recurrent unit. It's a model that, it's a type of RNN that has a latent state which has a probabilistic interpretation, and also continuous time dynamics, which means that we will be able to model irregularly sampled data. And to already give you a taste of what the main idea behind the CRU is, so basically, we assume that there is a latent state that evolves according to a linear stochastic differential equation. And so, okay, it's linear. This will make some of the computations easier, but overall the architecture is still quite powerful to capture nonlinear relationships between inputs and outputs, because there is an encoder and a decoder that relate our actual observations and the target output with this latent state. And so with this big picture in mind, which will hopefully become much clearer, so we will work out the details during the talk. But with this big picture in mind, let's like revisit this landscape again. So here, what is visualized is for typical RNNs. Let's assume that we have an RNN with like 3 latent dimensions. And they're here visualized in blue, green, and orange. And at these observation times, so an RNN has a recursive computation that defines how the latent state, so this 3-dimensional vector, is updated based on the latent state at the previous observation and the observation itself. But you will notice that there is no notion of dynamic between observations, right? So if we call the latent state ht, then it's a function of ht minus 1. And this is typically depicted in, here we can see an RNN cell. And one thing that I want to mention is LSTMs and GRU. One reason that they've become so popular is because they solve some problems, practical problems that you run into when you train an RNN. But the reason that they do that is that they have some complex and less complex internal mechanism to decide how much influence to give to the new data point in the update at time t. So roughly, I would call this a gating mechanism, which decide how much emphasis to put on like ht-1 or what's already encoded in the latent state at time t-1, versus how much emphasis to actually put on the new observations. And this, I'm just pointing this out here because gating mechanism is also, we will discuss this later for our method. Yeah. Then there's also these methods. So for example, GRU decay, where they make some kind of assumption that between the observation, the latent states are simply decaying. So this reflects the, let's say, intuition that the longer you wait, the less relevant the history becomes, and the more emphasis you should put on a new observation. And so these models, they are, so they do have some notion of dynamics between latent states, so that's great. But on the other hand, it's like quite limited because it's this, it can only model these like decaying behaviors. Yeah, and then so this work on neural ODEs, some of the method, like for example, a latent ODE. Here, if we look at the hidden states of this model, they evolve according to an ODE, so there are dynamics, but they're not actually influenced by the observations. And so what we actually want, and so there's a number of methods that do have this kind of structure, is that there is a notion of dynamics between the observations. So the hidden state have some kind of a life of their own. But whenever there is an observation, so here we have these like 3 observation points, the hidden states get updated. Okay. And so finally, so these neural ODE-based methods, they usually rely on ODE solver for the forward pass, and then either backpropagating through the solver or the adjoint method for training. And so this makes them quite computationally expensive. And similar, here these deep, let's say deep Kalman filter-based method, they usually rely on some form of approximate inference. Again, something that is slowing them down. And on the other hand, our approach to CRU from like these existing methods, it's the only one where both our forward pass will all be in closed form computations. But we still will be able to achieve this continuous time latent state, which will allow us to process time series at irregular time intervals. And so here is a summary overview of what the CRU is. So on the one hand, it assumes a continuous latent state, which will allow us to process irregular time series. The latent state is linear, so it's a linear SDE, and this will be important because it will allow for closed form computations of the forward pass. This closed form computations will be derived based on a continuous discrete formulation of the Kalman filter. And so through the Kalman filter update equations, we have a gating mechanism that somehow tells us how to optimally handle observation noise, at least in the latent space. And finally, something that I will talk about, which is maybe one of the main contributions of our work is thinking about how to best parameterize the CRU such that we get a good trade-off between modeling flexibility and runtime. Yeah, and so this is basically the outline for my talk. So far I gave a little bit of motivation and an overview of the related work. And now my plan is to dive in and actually discuss the architecture in detail. And based on the derivations, we will arrive at like an algorithmic description that tells us how to execute a CRU. I will also discuss then how like an efficient parametrization scheme, and finally show you our empirical studies and our findings. Yeah, are there any questions so far?
Maja, one question. Could you kind of explain once more the meaning of this kind of continuously interpolated function that you learn? Has that the interpretation of a rate, like sort of like the probability of an output if you integrate it?
Okay, so yeah, let's talk about this. So basically, we assume that inside the cell or inside the CRU, there is a latent state that is evolving according to a linear SDE. So here A is the transition matrix, and so the beta is a Brownian motion, and G is the diffusion coefficient. And so for this kind of dynamics, at each time point, we have a mean and a covariance that it like depends on the realization of the latent state, but we basically have this kind of linear SDE. We can also, if we start with some initial conditions, then we get a mean and a covariance at any given time point. And we will later see that it's exactly this mean and the covariance that play or that kind of describe the internal parameters of our CRU cell.
Hey, thank you.
Does that help? Or?
Yes, absolutely. Thank you.
Okay, great. And then, so we further assume that we have latent observations from this hidden state. And so they are noisy in the sense that, there's an associated observation noise, diagonal with sigma t ops. And maybe the kind of counterintuitive things here that they're also considered latent observations. And so what we mean by that is, so they are observations of this SDE, but they're not exactly the observation, they're not exactly the data. Instead, the data, the observed sequence gets encoded to give us the latent observations, which are the observations of this SDE. So at each time point, or for each observation that we have, there is an encoder f theta that maps like xt to what we call the latent observation yt, and it also produces this observation noise. Then Stefan, as I already alluded to, there at each time point there is a distribution over what zt is. And so we distinguish between a prior and a posterior. And the reason we do that is because, so if at time t, we can think of what the distribution is given that, like, given all the past encoded history and the past states. And that would give us the prior at time t. But then there's also a posterior that takes into account the new observation xt. And yeah, the parameters of the prior and the posterior, we distinguish them here with the minus and the plus. And yeah, we'll see how they are computed from the linear SDE. And then finally, at each time point, there's also a decoder which maps the posterior mean and covariance to a desired output. And now, since the latent dynamics are linear, and this latent observation model is Gaussian, we can basically apply to compute prior and posterior, we can apply a continuous discrete formulation of the Kalman filter. So specifically, so here we introduce this notation tau of t to get the last observation in our index set of observation times. So basically, this is the mu tau of t plus is the posterior mean from the last observation. So the predict step tells us how to simulate the dynamics forward to get a prior at time t. So this would be mu t minus. And then kind of a Kalman update step tells us how to integrate this new observation that's encoded into the posterior, into the prior to get posterior mean and variance. Yeah, and so now I will, maybe, are there questions about that? And also, Stefan, maybe this makes your question clearer of now what the role is of this linear SDE.
Yeah, thank you. Definitely helped. Yep.
So my plan now is to basically derive this predict step and the update step. And if there are any questions, feel free to interrupt. But basically what will come out is that those two computation steps can be done in closed form because of the modeling assumptions that we made. But because of the encoder and the decoder, we still get some kind of nonlinear relationship between input and output. And so first of all, let's talk about the predict step. So here we assume that at the last observation, which is tau of t, so that's the last observation before t, we have this random variable z tau of t. Then this equation tells us how to simulate the SDE forward until time t to basically give us zt. So this is zt at time t. And from that, we can compute both the mean, the new mean, and the new covariance, which in this case we consider a prior because it's not yet, the new observation is not yet integrated into it. But yeah, here would be the expression for the prior mean and the prior covariance. And yeah, so you will notice that here there's still some kind of integration. It's still written in terms of integration, but this integration too we can write in closed form. It's just, it takes a few lines to write it out, so that's why it's written here like this. So it's computed based on matrix fraction decomposition. And so the point here is that both the mean and the covariance are achieved in closed form. One thing that I want to point out, that the most expensive computational operation here is the matrix exponential. So for example, in the mean, we have exp of a times the posterior mean from the last time step. And so this will become relevant later when we think about how to make the computations fast. Yeah. Anyway, so we summarize the predict step in the following, just with the following notation. So we say that the prior mean, the prior mean and covariance at time t are a function of the posterior at the previous time step, as well as the amount of time that has passed. Now, the update step is a little bit more familiar, maybe to anyone who's seen the Kalman filter before or has just done a lot of Bayesian inference. But here, now we use Bayes rule, multiply the prior with the likelihood, and because they're both Gaussian, we get the posterior. So, right, the observation model is also Gaussian. And here the posterior mean is the prior mean plus the Kalman gain times, let's say the prediction error. And the Kalman gain is a quite interesting quantity. If you notice that if it's, for example, 0 or close to 0, then the posterior is the same as the prior. And only if the Kalman gain is non-zero, then the new observation is somehow taken into account in the update. And so this, I'm pointing this out because I was already mentioning gating mechanisms earlier, but it's really the Kalman gain which tells us how to optimally balance information already encoded in previous hidden states with the new observation. Yeah, and it also appears here in the covariance. And about runtime, what is to notice here is that the most expensive computation is the matrix inversion of the Kalman gain. But still, everything is in closed form. And so again, we can simply summarize this as that the posterior time t is a function of the prior and the encoded observations. Yeah, and so now we can basically look at what how the CRU processes input sequence. So this is now a simple summary that basically at time t0 or at any time point, xt gets encoded to get the latent observation and observation noise. Oops. Then based on the latent observations, we can perform an update step. Then the predict step tells us how to simulate forward to the next time point. And finally, the decoding step tells us how to take posterior mean and covariance and produce the output. Yeah, and so as promised, we now arrived at basically an algorithmic description of how to apply at least a forward pass of the CRU. And what I would like to discuss next is how to efficiently parametrize the CRU. And the reason why this is so important to think about is that obviously there's always a trade-off between modeling flexibility and runtime. So for example, here, because we're making these linearity assumptions for the linear SDE, obviously that limits the types of dynamics that we can capture. But because we get the closed form computations, this gives us such an gain in runtime that we might be able to, for example, increase the latent dimension. And suddenly, maybe the modeling flexibility is not that bad because the latent dimensions are large. And so what I will discuss now are basically is a strategy how to increase modeling flexibility without hurting runtime too much. And then I will discuss a way how to parameterize the CRU that reduces runtime without hurting the modeling flexibility too much. So specifically, one thing that we do, and this is also done in several related works, not just this one, but so this is Becker et al. 2019, but in several related works where they work with some kind of linear transition models, instead of basically use a locally linear model. So here, the transition matrix A is no longer time invariant. Instead, it's a weighted sum of k basis matrices. So typically k could be, let's say, 10 or 20 or something like this. So we have these like 10 basis matrices. And the mixing coefficients are a function of the latent state. And specifically, we take the posterior mean, mu t plus, and then it goes through a small neural network with softmax activation. So as output, it produces these mixing coefficients. And so this is, for example, like this is something that increases the modeling flexibility of the model because it's now no longer time invariant and linear without hurting the runtime too much. Yeah. On the other hand, to reduce runtime, let's recall that the most expensive computations that we have are both the matrix inversion. So this was in the update step, so for computing the Kalman game. And then on the other hand, we have the matrix exponential, which is part of the predict step. And again, so the matrix inversion, for the Kalman game, it's also computed in other approaches to deep Kalman filters, specifically Becker et al. There, what they do is they parameterize the basis matrices of this locally linear model in block diagonal matrices, and also make some assumptions about how the covariance matrices are structured and so forth. And what happens is that really reduces the, so they don't have to do the full matrix inversion, but they can basically do it in blocks. And this gives them some gains. And so we also employ their strategy. But in addition, we have the issue that for the CRU, because we are we are propagating this SDE forward, there appears the matrix exponential. And so I would say that this is almost the main contribution of our work is that we figured out a way to parameterize the transition matrices in a way that allows us to compute the matrix exponential more efficiently. And the way to do that is to parameterize the basis matrices in terms of their eigenvectors and eigenvalues. So we restrict each of the basis matrices to be symmetric, which means that they decompose in this way into an basis of orthogonal eigenvectors, and then also a diagonal matrix of eigenvalues. And not only that, we further restrict all the AK to share the same eigenbasis. And so what this does is then we can, instead of having the matrix exponential of a sum of matrices, what happens is that we basically use the eigenvectors to project the latent state into this space where the dynamics are orthogonal. And then we can apply, instead of the matrix exponential, because now the dynamics are orthogonal, we can apply element-wise exponentials along the diagonal, like the normal exponential function. And this gives us a huge saving in runtimes, as we'll see here. So this is for one of the data sets that we analyzed in our experiments. Here on the x-axis, you see the dimensionality of the latent state. And then on the y-axis, how many seconds it took on average to train for one pass over the data. And yeah, so the CRU, which also contains all the approximations that were done in previous work, like for example, Becker et al. It has a much worse runtime, especially as this dimensionality of the latent state increases. And with f-CRU, so we call this the fast CRU, we get significant increase in runtime, decrease in runtime. Yes. Good. So I want to mention how this is trained. So I'm just mentioning this because sometimes for Kalman filters, people assume that the dynamics or so are fixed, but no. So we have the following parameters. So there are the parameters of the encoder and the decoder. And then for the locally linear SDE, we actually only train the following parameters. So it's the diagonal Q of the diffusion matrix of the Brownian motion. And then the network's parameter phi for producing the mixing coefficients for the locally linear model. And finally, the transition matrices AK. And so all these parameters, they're just treated like, let's say, neural network parameters or so, and trained jointly on a negative log likelihood loss that compares. So for a given input sequence xt, the CRU produces the outputs OT with variance sigma. And this is compared to, like here, ST stands for the ground truth sequence. Yeah, and so if it's real data, then we use Gaussian. If it's binary observations, then we would use instead the Bernoulli log likelihood. But this is basically the principle behind training. For the f-CRU, the only difference is that the basis matrices, instead of parametrizing them directly, the parameters are these diagonals, so the eigenvalues, and we need a set of orthogonal vectors E, which is basically the eigenbasis. And so we use a Python package by Casado for how to maintain these orthogonality constraints in E during training. Great. Are there any questions at this point?
I have a few questions, but I think I'll wait until the end of the talk. Thanks.
All right, sounds good. What I wanted to describe now is basically our empirical study. And we studied 3 data sets. So first are noisy pendulum images. So those are 24 by 24 frames from a pendulum simulation. And there's some correlated noise process that's put on top of the images. Then we also study the US historic climate network. So this is climate data from over thousands of stations across the US, over many years. And finally, we also study health data, specifically PhysioNet. That's a 40-dimensional time series. Yeah, and just to show you how at some points, you know, it's kind of partially observed. And these different observations, they occur at irregular time intervals. You basically see how it evolves over time for a few of these 40 variables. Yeah, and this is for patients that are in the ICU for 48 hours. Yeah, and so we study the CRU in comparison to a few methods on 3 different tasks. So on the one hand, interpolation, regression, and extrapolation. So for example, in the interpolation task for the pendulum images, we have a sequence of length 2000. No, sorry, the sequences are of length 50. But yeah. So sequences of length 50, and then the input sequence is you obtain by randomly dropping half of the frames. So we have an input sequence of length 25, which is a subset of our target output, which is of length 50. And yeah, we compare the CRU and the f-CRU to a number of different models. So on the one hand, we have the GRU and the RKN, which are inherently models for discrete time. So here we compare both with the model that just ignores the timestamp, but also here the delta t indicates that these 2 approaches, so GRU delta t and RKN delta t, they get as an additional input the time that has passed since the last observation. Yeah, and then we also compare to these 3, let's say, neuro-ODE based methods. And surprisingly, actually, the GRU and the RKN delta t already do quite well, but still both the f-CRU and the CRU outperform them in terms of MSE on held out test data. Yeah. And so we also studied the interpolation results on the climate data and the PhysioNet data. And here you will see that there are even like much larger gains in terms of runtime. So one reason is that the pendulum simulation, the timestamps were still kind of regular, whereas in these data sets, there's a much higher variation in how large the timestamps are. And here somehow the ODE solvers then require a larger factor of processing time, let's say. And so we see an improvement in runtime, especially when we look at the f-CRU. But also we get higher held out interpolation accuracy. Yeah, and one thing that I find quite interesting is, you know, for example, the f-CRU, even though it's like twice as fast as the CRU, the results are in this experiments, they were almost comparable. And so it's not that hurtful on these data sets to kind of restrict the transition matrices to be symmetric and to share the eigenvectors. Yeah, then so here is a visualization of the Kalman gain on one of the test sequences for a regression task. So here the task was given input images and a target output was the angle of the pendulum. So the target is to predict the pendulum. And what we did here is basically visualize the Kalman gain that the CRU associates with each of the frames. And one thing that you can notice is that the lighter, the smaller the Kalman gain. And as a reminder, the smaller the Kalman gain, the more emphasis is put on the prior as opposed to a correction term based on the prediction. And yeah, so we can see that, yeah, in these frames that are somehow much clearer, or especially, for example, this frame, which comes after a sequence of noisy frames, the model puts much more emphasis on by having a darker or a higher Kalman gain norm. Yeah, and so finally, we also studied, as I mentioned, the extrapolation task. Here, the input sequences are the first half of the sequence, and the target is the second half of the sequence. And here, actually, on the PhysioNet data, the ODE RNN achieved the highest accuracy. On the climate data, it's our method. And yeah, so but let's say we're still competitive. And one last thing that we looked at is not just how the gating mechanism works under noise, but also how it works under partial observability. So for the climate data, the inputs are around 1,000 dimensions. So here on the y-axis, you see different sparsity levels at which we dropped observations. So we take a sequence, and so like an input sequence, and at each time point, we randomly first sample a percentage between 0 and 100, or like at this scale, 0, 20, 40, 60, or 80. So let's say it's 60. So that means that we are dropping 60% of the observations. So now what this gives us is a much sparser input signal, where at each observation time, we have a level of sparsity between 0 and 80%. And now what we can look at is, again, what the norm of the Kalman gain is for those observations, and visualize this in these histograms based on the sparsity level. And what we can see that for sparsity level 0, the Kalman gain norm is highest. And then as it increases, like 20%, 40%, 60%, it moves slightly more and more to the left. And there's also, it's interesting that it somehow looks like a bimodal distribution. We don't quite know why. But yeah, especially for 80%, it's like this left mode of a lower Kalman gain norm that is much lower. And so this means that especially when there's a lot of information missing, that the update takes the prior stronger into account than when there's more value in the new incoming observation. Yeah, so based on that, I want to summarize my presentation. So I presented the CRU, which has a linear but continuous latent state with closed form updates. We have seen that it has a gating mechanism that somehow optimally tells us how to handle noisy latent observations. And finally, I also discussed efficient parametrization and how it affects the trade-off between modeling flexibility and runtime. And especially with the experimental results, we also saw that often, even though the fast CRU gives us a large improvement in runtime, it doesn't hurt the RMSE results too much, meaning that it still provides adequate modeling flexibility. Yeah, and so this concludes my talk. I'm excited if you guys have questions to continue the discussion. Also, feel free to contact me under the following email address. Thank you.
All right. Yeah, I don't know if Eric or I should organize the discussion.
Either way, I think we're all virtually thanking Maja, and there's room for time for questions. Either if anyone has one, you can just unmute and ask, or you could also type it into the chat window.
I think I have one question, if I may ask. So if I got your model correctly, right? I mean, it's basically a linear Kalman filter between observations, or at least the dynamics is a linear diffusion process in between observations, right? And then when you observe something, then you kind of non-linearly transform the diffusion coefficients, right? The mean and the variance, essentially, right? So to just kind of understand correctly, so this does not allow you to predict the next emission, right? So you cannot use it as a generative model in this sense. You cannot predict when the next observation will happen in the future, right?
That's true, yeah. So we don't have a mechanism that tells us or that considers when the next observation will happen.
Okay.
Yeah.
And when you do interpolation, right? Strictly speaking, if you're kind of in between two observed values, strictly speaking, this interpolation should trigger a nonlinear transformation, right? Do you take this into account, or do you kind of just interpolate linearly, so to speak, and then just report that corresponding output?
Yeah, so, right. So if at time t, we want to produce an output, but we don't have an input, then the posterior is the same as the prior.
Mm-hmm.
Yeah, so we simply simulate the dynamics forward until this time point and then have the emission. So the nonlinearity only comes from the decoder at that point.
Okay.
I think, Roy, do you have a question?
Yeah, thanks. This is really beautiful work. I was wondering if did you make any attempt to keep the eigenvalues close to 1, or maybe at most 1? Otherwise, right, if you have very different time scales, things could explode or vanish, right?
Great. Yeah, so we actually didn't constrain this eigenvalues in any way.
And don't you find that things sometimes explode?
Yeah, we didn't. Actually, we found it quite stable, but it's a good point.
Interesting.
I will ask Mona, who ran the experiments. Yeah, we actually found it much harder to get. So in the experiments, actually, we found our method more stable than the neural ODE-based ones. So especially with the pendulum images that are like really high dimensional, right? And so while there is a clear underlying physics on the scale of the state space, of the velocity and the angle of the pendulum, we are considering the images. And so this was quite hard for the neural ODE-based methods to capture. And so what we did there is that we also empowered them with the same encoder and decoder that we use for the CRU. And then for some of them, they actually worked better with the encoder and decoder. The others, it was unstable. And so then we always reported the better of those two options.
Nice. And thank you. And another question, if I may. So if I understand correctly, in the end, this whole model is deterministic, right? There's no stochasticity.
Yeah, yeah.
So like there could be, right? You in the end you have this a distribution that you just take its parameters in a deterministic way. So have you considered using that as a stochastic model?
Yeah, I think one interesting way to add stochasticity would be to decode, when you decode, instead of using the mean, you sample and produce a few decodings or something like this. Yeah, but in terms of how the stochasticity is handled between, like the cool thing is that the Kalman filter tells us that it's like the optimal mean and covariance update.
It's fantastic. Thank you.
Looks like we have one more question from Mike.
Yeah. So I know these stochastics is these linear, study the same types of things. And I know there's general results that says you get stationary measures, which is the Gibbs distribution for like your ZTs. So, and if you have like the Lyapunov function, you get the stability, you get convergence to that from any state. So I was just wondering, did you use anything like that in your stability analysis? Or how did you do you have any proofs of like the comment you just made about how you notice your processes were pretty stable over time, or was this just something more empirical that you observed?
It was something empirical. So you might be more familiar with this than me. So how would you do a stability analysis? What would be the big picture?
Yeah,
for example,
yeah, well, the models I look at reflecting motion. So I would not have a domain like you did of all of Rn. So I would have like a hypercube, right? And there are stochastic processes which you can reflect on the walls, and there's a lot of papers on this. And there's a paper in 2014 that showed, right, even and this proof applies if you remove the reflection. For that type of system, you get a stationary state, and I even know what it would be. Your AZ, your drift was A times Z. So your stationary state would be a Gibbs state, be E to the, and then it would be your temperature, your coefficient of your noise times the quadratic form Z, and then parentheses A plus A transpose, and then close parentheses Z, and I think a 1/2 in front of that. But I mean, there's explicit, the point is there's explicit formula for the stationary states. And then you could use that if you were doing time averages of your of these random variables. You could use if you get quick convergence, you could do away with your Green's function to propagate your stochastic variables, and you could just draw from that stationary sample, which would be much faster. So those are some tricks you could use. I mean, I kind of do some similar things. And I'm looking at that for applications and a problem I'm doing at work, in fact. But yeah, if you study that, I mean, if you want, I could probably forward you some papers. I'm not sure that you need it though. I mean, but I was just curious in terms of the stability. I mean, if you could just run it and see if you're getting stable states, you could almost test that empirically just from like sampling, right? So. But it's kind of a nice theoretical result.
Thank you so much. This is super an awesome impulse for me to take this next. So practically we didn't have issues, but obviously it would be awesome to do something that's even theoretically more sound. So yeah, it would be great if you could forward the papers.
Okay, I'll write your email down. I could forward you some of those references. I'd be glad to. So, all right.
Thank you, Mike. Yeah, I'll just observe that coming back to the question Roy had. I think that the stability property of a system like this might depend on what the inputs look like. Sort of right? She's conditioned on this point process. So you might need to say something about that more explicitly to be able to talk about stability. But definitely interesting questions. So,
but I guess then you could constrain the encoder to give you outputs that follow exactly those requirements that you would have of the inputs.
Yeah.
So that would be interesting.
Absolutely.
So yeah, I hadn't even thought about that direction. So I'm really grateful for you guys for that inputs.
Great. Well, we're at oh, we have one more question in the chat. There's a question about, so for medical data, where you're more likely to have observation when the patient is sick, how do you expect that we could see this from the parameters that we would learn from your model, right? So how would that be reflected in the types of ways your parameters would be learned if you had data of that sort?
That's a very great question. And so I haven't done a qualitative analysis to look what actually happens. I can just speculate. And my speculation would be the following, that one way that a model like this would have the capacity to capture this would be to take one or a few of the dimensions and basically capture how much time has passed since the last observation. So it could be basically a few dimensions that have these kind of decaying parameters. And then, yeah, now when a new observation comes in, this one latent state tells us that it's been a really long time since blah, and then this would correspond maybe to a healthy patient. But that being said, that's speculation.
Okay, great. Well, we're a little past 2, so I think we should wrap up there. But let's all thank Maja again for a very interesting talk.